This is an activity that we would do together. Unfortunately, the materials and our inability to be together prevents that. But I'd like to show you really quickly this simple strip down motor. I've assembled some stuff, a little cup, some 120 grit sandpaper, a dowel I'm going to use to wrap the motor armature with. I got a Sharpie over there, pair of scissors, a couple paper clips. You can do this with less voltage than the 9-volt battery, but I kind of like to use the 9-volt, and I have a little battery jacket that snaps on top. And I have some ceramic disc magnets that we're going to use in a little bit. So I'll start working on this. I got this, it's called magnet wire, and it's actually enameled. It looks shiny and metallic to you probably, and it is, but it's actually an oil-based enamel, I think, that's on top of the wire. So this wire is actually insulated, even though it looks almost copper colored to you perhaps. I'm going to peel off some of this wire. I wrapped the wire around this dowel just to make a nice circular loop, and I'm going to slide it off carefully. Now, as I spoke about a minute ago, the wire actually has a coating on it. I probably could have done this ahead of time, but I'm taking the sandpaper and gently removing that enamel. I don't know if you can tell the difference in color, but I've gotten it down to the copper. I'm going to do that on both sides. I think I've successfully removed a good amount of the enamel there. I'm going to try to make this into a circle again as best I can. And I'm going to wrap the wire itself around the loop just to give me confidence that it's going to stay together. The one thing that's important about this armature I'm building, or the loop, is that it be balanced. I'm going to open these up and make little stirrups for the armature to sit on. I want them roughly at the same height. That looks pretty good. I can tell it's a little top heavy a little bit, so I'm going to adjust a little bit. The instructions tell us to actually blacken the top half of one of the stripped wires with the Sharpie. So I've done that to the best of my ability. I'm going to put the 9-volt battery jacket on the 9-volt battery. And before I connect it, I'm going to put some magnets to provide the necessary magnetic field. I'm going to put a couple inside and a couple on top here. I can tell it's not perfectly balanced, but I'm hoping we're going to get some action anyway. And here we go. I made a second armature that was just slightly lighter weight. The first one I made, I felt like was just too heavy and too thick. So I made another one, and as you can see, it works quite well. That's all there is to it. Because the current's going one way on one side of the wire and on the other side on the other wire, there is a torque or a unbalanced force that causes the coil to rotate. And get you to understand why I put black Sharpie on top of 1/2 of the armature that I made with the magnet wire in the lab. And one more thing too, I want you to try to understand that even though we've been using dots and crosses for the magnetic field when it is either into the board or out of the board, we can do that for current as well. Imagine you had a wire and it's coming out of the board, it's perpendicular to the board. Well, that wire, if the current is flowing toward you, could be indicated by a cross section of the wire. The circle is just like a slice of salami, a cross section, and the current's coming at us. Or conversely, if the current were going away from you, X's would represent the direction of current in this wire. Also, you notice that I've drawn sort of my best rendition of like a loop of wire that's laying in a magnetic field. Again, Keishlai will never forget, but the magnetic field by definition goes from north to south. Okay, so let's explore what's going on at a couple of different moments in time. Now, on your sheet of paper, I'm not so much worried about the front side as I am the back side. On that sheet of paper that I provided you, I'm going to draw these different situations at different times as the loop rotates, and we're going to explore what's going on. At time equals 0, so to speak, we got a wire on the left side and a wire on the right side. Remember, it's really a loop. It's going in and out of the magnetic field, but I'm just representing two cross sections of that wire. Because the left side, okay, so the armature of a DC motor has this thing called a split ring commutator. It is a ring that is not entirely complete. And these little brushes are the connectors that touch the commutator and commute the electricity. The left side is connected to the positive terminal. So current in this moment is going to be going in on the left side of the wire and out on the right. So I'm going to draw a cross here and a dot there. Let's use our right-hand rule to evaluate the direction of the force. Magnetic field, again, north to south. I'm going to use my thumb as the current because current is moving charge, right? So I'm going to stick my thumb in for this wire that I'm going to label it wire 1, and I'm going to label this wire 2. They're really different parts of the same wire, but I want to be able to refer to it later in case it's moved. So on wire 1, the field is north to south, the current is in. The force on that one is down. This one feels a downward force. Conversely, the one that has got current coming out of the board, feels an upward force. And they will rotate under a torque till at time equals 1, wire 1, which had current going into the board, is now on the bottom, and wire 2 is now on the top. Now, if the current were still out on this one and in on this one, which it was a moment ago, the forces on this loop would be up and down, and that motor wouldn't turn. It would be stuck. All's well and good as long as the force on the left side is up and the force, the force on the right side is up and the force on the left side is down. But if that continues to be the case, it's going to get stuck. It's going to go, and the force is up here and down here and it ain't going nowhere. That's where the Sharpie comes in. That's where the split ring commutator comes in. Because once it's rotated 90 degrees, these gaps, or in the case of the black Sharpie, some insulator, because the Sharpie's an insulator, doesn't conduct electricity very well, dry Sharpie. So at this moment, there is no current, and there is no little red force, but it is already moving. So it continues moving to the point at time 2, where now wire 2, this is moving counterclockwise, wire 2 now is on the left and wire 1 is on the right. But these brushes don't move, the ring moves. And so now what I was calling wire 2, which was on the right, and wire 1, which was on the left, they've switched places. And the current actually, remember, the left side of this loop, regardless of whether it's wire 1 or wire 2, this has always got current going in because it's connected to the positive terminal. So we're going to have X here and dot here. Notice that the current is actually switched direction. Wire 2 used to have current coming out of the board, but now it's moved over at 180 degrees and current is in on the left side of this configuration. Well, we've already used the right-hand rule. We know that when the current is in, the force is down, and when the current is out, the force is up. And so this continues to rotate. Now there's a net torque on it. And at time equals 3, wire 1 will eventually reach the top, wire 2 is on the bottom. But at that moment, the split ring allows the circuit to disconnect. There is no current here, but it continues to move based on its momentum. And this cycles through and allows a DC motor to continue to rotate effectively in a constant magnetic field with a direct current doing the moving of the charge.